All right, so we're going to finish up today by talking about what you can do when you write a complex number in trig form. Okay, specifically, what's easier to do. And what ends up being easier are four things: multiplying, dividing, raising things to powers, and taking roots. If you were going to do division the old way, okay, I'll quickly go through an example. This is not trig form, this is standard. But does anybody remember what you'd have to multiply top and bottom by? The conjugate. Now what's nice is the top isn't even two different terms, right? It doesn't have, or I mean, it's two different parts. It doesn't have a real part, and it doesn't have an imaginary. So when we multiply by 5 minus I, the top actually isn't too bad. It's a single distributive. If the top had a real and an imaginary, we would have to FOIL that out. But we don't have to. So at the top, we get 15 minus 3i. And in the bottom, when you FOIL all that out, you will get 26. And if you're not sure how to do that, you'd have to just go through and do 5 times 5 and do everything else. But you will get 26. Now, the last step would be to write it in standard form. 15 over 26 minus 3 over 26. So not too bad, because I used the trick to multiply the conjugates really quick in my head. And I didn't have that bad of a distributive property in the top. But if you didn't remember that trick, and you had to FOIL all this out, it's going to take a little bit longer. Okay? Especially if you don't know the trick here, because then when you FOIL it out, you're going to end up with I squared. Then you got to remember to change I squared to -1. Then that's going to cause you to have some like terms that need to be combined. So it ends up taking quite a long time, potentially, to multiply and divide complex numbers in standard form. But when we use trig form, all of that goes away. We don't have to do any of that to multiply and divide in trig form. So let's say we had two numbers in trig form. Each number has its own radius. We'll call them the first one and the second one. And they also each have their own angles, which I'll call theta 1 and theta 2. All we have to do if we want to multiply these two complex numbers together, we don't have to FOIL, we're not going to get I squared, we don't have to use conjugate, we don't have to do any of that. All we have to do to multiply these together is multiply the two radii that you have together. That gives you your new radius. And then add the two angles you have together. And that gives you your new angle. And that's it. So all you have to just multiply the radii, add the angles together, and that takes the place of all the FOILing you have to do to multiply them all. Let's see. Now dividing, I just went through that. Okay, I showed you what happens there. You got to use the conjugate, you got to FOIL it, combine like terms, all that stuff. Well, if they're in trig form, we have a formula that's very similar to what's up above. We just have to tweak it for division instead of multiplication. Up here, we multiplied R1 and R2. Anybody have a guess what we're going to do with R1 and R2 down here? We're going to divide them. Yep. So to divide two complex numbers, your new radius in trig form is the quotient of the original radii. That's how you get that. And how do you think I'm going to get my new angle? I'm going to subtract them. Now, of course, when we do division, you can't divide by 0. So R2 would never be 0. this formula takes the place of everything that we just did on the other page. Now, the key is your numbers already should be in trig form to use this. If they're not in trig form, it's probably going to take longer to change to trig form, do it that way, than it would to just multiply top and bottom by the conjugate. So if I had to do something like this, I'm just going to multiply top and bottom by 8 plus 5i and deal with all of that. I'm not going to change this to trig form, change this to trig form, and then use that formula. So this formula is really only faster if the numbers are already given to you in trig form. All right, let's try an example. So what I've done here is I picked two numbers. I think we worked with one of these before, -2 plus 2i. I think that was one we did right here. So we converted that to trig form yesterday. What I did is I just copied down our answer and I changed it to a decimal. Okay, well we did this one yesterday. This one I think we did one like it in the homework. I remember there was a problem with a radius of 5. But anyway, they've given you the trig form of each number. Okay, so they want us to find the product of these two numbers and the quotient. Now, let's do the product and the quotient using the trig form, and then I'll quickly FOIL these out and show you that it comes out the same. I'm not going to divide them because that takes a little longer, but I will FOIL these out and we'll see that it's the same. All right, let's start with Z1 and Z2. How am I going to get my new radius, or what do I do with the old radii to get the new one? I multiply them together. So what's 5 times 2 square roots of 2? 10 square roots of 2. So there's my new radius. Cosine plus I sine. And what's going to be how do I get my new angle from my old angles?
Add 2.36.
Yeah, add 2.36 plus 0.93. So that gives me 3.29. And that's it. And that's in radians, because there is no degree symbol on this angle. Now, what if I know they didn't here, so this is the answer. But what if they did say to change that to standard form? How do you take that and make it standard form?
I did not know how to do that.
And multiply R with each, and distribute them.
Just distribute it out. So if you want to know the real part, it's 10 square roots of 2 times the cosine of 3.29 radians. So that's negative, it's basically like negative 14 if we want to round it up. So it's like negative 14. And then 10 square roots of 2 times sine 3.29. Sine 3.29. And that would be about negative 2.1, roughly. Just rounding it.
Sorry, how did you do it?
Just distribute out 10 root 2.
Oh, I see. It's asking.
Now, the reason I did that is because now I'm going to FOIL these out the way we're used to doing it and see what we get. So let's try it. So 3 plus 4i and negative 2 plus 2i. This is the only one I'm going to do twice. Other than that, we're just going to trust that the trig form, it works. All right, what's 3 times negative 2? And then 3 times 6i. And then negative 8i. So it might not come out quite exact because we had some rounding in there, but it's close. If we went to more decimal places, it would have been better. And then what's 4i times 2i?
8i.
Squared.
Yeah, sorry.
So that's negative 6. And what's 6i minus 8i?
Negative 2i.
So negative 2i. And 8i squared?
Negative 8.
Negative 8. And what's negative 6 and negative 8? Minus 2i. So negative 14 minus 2i and negative 14 minus 2i. Again, it's because of the rounding on this angle that we didn't get exactly negative 2. But the point is, FOILing it out or doing it in trig form, you get the same answer. And I think trig form is fast.
Are there going to be questions on homework that are asking to find standard form or trig form? Or are we going to do more practice with that? Or is that something?
I don't know how many, because that was on last night's homework, but yeah, that is on the test, converting something like this to something like that.
Those 4 minutes.
We might do another one. I guess we could. We'll do this one. Okay. Now I want to divide these two complex numbers. What I don't want to do is multiply top and bottom by negative 2 minus 2i, the conjugate. That's going to take a while. We're just going to use these. So to get my new radius, what do I do with my old radii? I do what? I divide them. 5 divided by 2 square roots of 2. That's my new radius.
So it's 5, it's just 5 root 2 over 2.
So we've got to fix that. So that's 5 root 2 in the top. And what's in the bottom? 4.
Oh, yeah.
So my new radius is 5 root 2 over 4. And how are we going to get our angle? Subtract 0.93 minus 2.36. So 0.93 minus 2.36. Negative 1.43. Now, technically, that is trig form. Okay, you've got r and you've got an angle. But what if they said they wanted the angle positive? What could we did this in degrees, I think, in the homework. Yep.
Oh, at 360 degrees.
If we were doing degrees, we could add 360, yes.
Oh, that's 2 pi.
We could add 2 pi to that.
How do we know that we're in radians?
There's no degree symbols on any of the numbers. So as a positive angle, it's 4.85. So 5 root 2 over 4. Cosine 4.85. And this answer is also correct. And there's a third way to do it. So we've talked about having negatives inside the argument, depending on if it's sine or cosine, and you can do something with that negative. If you have a negative inside your argument to a cosine function, what could you do with that negative? You could just get rid of it. Because of cosine, the way it works, the negative inside the argument doesn't matter. So we could just wipe it out. So you could also say cosine 1.43. And what about a negative inside a sine function? You cannot just get rid of it. But what could you do with that?
Do you move it to the front of the sign?
Yeah, you can move negatives to the front. Okay, that's an identity we learned. So we could say minus, when you put that in front, I sine 1.43. Now, I'm not going to ask you for all three different answers, but the point is, if this was a multiple choice problem, and you see an answer like that, and you did all your calculations and got that one, well, they're the same thing. You just have to know that they're the same.
Isn't it? Wait, why is it minus? Oh, just
So this last one is probably the easiest way most people think of to get rid of a negative. This middle way. Then the last way is a little bit more sophisticated because you're using an identity to get rid of the negative. Okay? We're canceling it out completely, and then we're moving it in front. So, any questions on that? Usually negatives don't come up when you're multiplying unless they started you with a negative angle. Because when you're multiplying, you're taking these two numbers and you're adding them. So if they started you with a positive and a positive, when you add them, you still get a positive. But with division, if they gave you one that was smaller for the first one and bigger for the second one, then when you subtract them, that's when you run into the negative. And the other thing you can run into with division is you can get a square root in the bottom, and you have to fix it. Where multiplication, you'd never end up with a square root in the bottom because you're not dividing them, you're multiplying. Any questions on how we got those? And if you wanted it in standard form, you just take 5 square root 2 over 4, multiply it by the cosine, and take 5 square root 2 over 4, and multiply it by the sine. Okay, so does anybody want to see anything else with, actually I think I had one more anyway. All right, we'll do this one and then we'll move on to the last thing. Now, this one, they did not start me off in trig form. So if I was going to do this problem, I would probably just do it in standard form, but the directions specifically say to do trig form. So we have to do trig form. So let's start with negative 2 plus 2i. Let's convert that to trig form.
Do you know why they haven't used z?
We already have. Let's, since we did the last one in radians, let's do this one in degrees. And even though we already have this one from the previous page, let's just practice it again in case people don't remember how to do that. So we've got left 2, up 2. You know, this side is 2, and that side is 2. Yeah?
Does your scanner work with previous year's IDs?
Yes. So how do you find your absolute value? Use the Pythagorean theorem. So what's the length of the radius? This side is 2 and 2. 2 root 2, or yeah, square root of 8. So your radius is 2 root 2. And what's the formula to find the angle if you're in quadrant 2?
180 minus the thing. No, sorry. I was thinking.
There's different ways you can think about it. Well, what's the way I showed you yesterday?
Pi plus inverse tangent y over x.
Yeah, and we're going to do degrees.
Yeah.
So 180 plus the inverse tangent of, what's y in this case?
2.
And x?
Negative
2. Well, that's the inverse tangent of negative 1. And what's the inverse tangent of negative 1 in degrees? That's a negative 45, which means the angle from quadrant 1 to my hypotenuse is 135. So 2 root 2 cosine 135 plus I sine 135. Okay, so there's our first one.
Thanks. What we're doing yesterday is just part of what we need to do to get the answer for things today.
Yes. All right, now we need 3 minus 3 root 3. Okay, so it doesn't really matter if you draw it to scale. All we know is, we're somewhere in this quadrant because we're going right 3 and then down 3 times the square root of 3. So draw a triangle. That side's 3. That side is 3 square root of 3.
Those in the I or something.
Yep, that's the down.
I.
So that's my y-axis. Okay, let's do Pythagorean theorem. What's 3 squared?
9.
And what's 3 square root of 3 squared?
Is it just 6? What?
It's 9.
9?
No,
this is 9 when you square it.
It'd be 9 times 3 is 27.
It'd be 27.
So you cancel out the, you square the 3 and then you get rid of the square root.
Yeah,
So that becomes 9 and then that
9 times 3. Yep, so 27. And now take the square root.
So isn't it 6?
6. Yep. So your radius this time is 6. But I need my angle. Okay, what quadrant am I in?
4.
And what's the formula for theta?
Just
Inverse tangent of y, negative 3 root 3. Should go back up in case you want to see it. Over x is 3. So might as well cancel those. It's the inverse tangent of square root 3. And we should remember that when we do inverse tangent with square root of 3, that comes out nice. Well, that's in radians, but we want degrees. So it comes out to negative 60. Okay, so the angle is negative 60, or if we don't want to deal with the negative, what can I add to it?
360.
Which would make it 300. So I'm going to use 300 as my angle. And if you wanted to leave it as negative 60, I guess you could, because it's not the final answer to the problem. It's just a piece of information we're going to use. Okay, now the quick part is to multiply these together. What's going to be my new radius when those get multiplied together?
Just 12 root 2.
12 root 2. And what's going to be my new angle?
So just 435.
435, which I can make the same as something else by doing.
360.
I can subtract 360. So when you add those together, you get 435, but that's the same as 75. There you go. So that's the product in trig form, which would have been extremely fast if these two numbers were already given to you in trig form.
Yeah.
That's the only thing that slowed us down. And the quotient. What's going to be my radius when I divide those two? Root 2 over 3. And how do I get my angle? Subtract what from what?
Minus 300.
Minus 300. Okay, so the angle is negative 165. And one way to make that positive would be just add 360. There we go, plus 360. So that gives me 195. much quicker if we start from the point where we already have the trig form to divide these two by doing this method than it would be to find the conjugate, FOIL it, combine like terms, change I squareds to -1s. We don't have to do any of that. And what if they didn't say it? What if they said to take one of these and leave it in standard form? How do you get this to standard? Yeah, you just distribute this out to the cosine 195 and to the sine 195. So any questions on multiplying or dividing? Okay, so that's 8.3. Okay, so we saw how to multiply in trig form. We saw how to divide in trig form. And now we're going to look at how to raise something to a power in trig form. Normally, I also look at how to take a root, which is the opposite of raising to a power. But we'll just look at raising to a power. So let's say that you wanted to raise something to a power, say a complex number, like this. 2 plus 3i to the third power. What does that mean to do? Like if you wanted to just write that out, not like the final answer, but write it without a power of 3. Yep.
It's 2 plus 3i times 2 plus 3i times 2.
Right. It's 2 plus 3i times 2 plus 3i times 2 plus 3i. And let's do that up. So we're going to we'll start with the first two. 2 times 2 is 4. What's 2 times 3i? And another 2 plus 3i? So it's 12i. And what's 3i times 3i? -9. And before we distribute again, it would be good to combine like terms. What's 4 minus 9? -5. Now we got to multiply it one more time. What's -5 times 2? And then -5 times 3i. So it's -15i. 2 times 12i. And what is 24i minus 15i? 9i. And 12i times 3i? -36. And now combine -10 and -36. Plus 9i. Okay, so not awful. I mean, I was able, we did that in maybe under a minute or so. But that was only to the third power. Now, if we had something like that, well, you're going to have to write in standard form 2 plus 3i 45 times, FOIL it all out. You may start to see some tricks, because now that we know 2 plus 3i cubed, you could really write this as a bunch of powers of 3, all multiplied together, and then actually 15 of them. So this problem could really turn into this to the 15th power, because we already know 2 plus 3i cubed. So we could kind of use some tricks to maybe simplify it a little bit, but still you're going to end up doing a real lot of FOIL. So we don't want to have to do this in standard. Okay, there's got to be a better way to do it, and that would be in trig form. So we'll come back to this one, and we will do it in trig form and see if we get the same answer, -46 plus 9i, because there's no rounding here. So that's an exact answer. So that's a good one to come back to. So the formula that we can use to raise a complex number to a power is called de Moivre's theorem. Now, the nice thing about de Moivre's theorem is it doesn't matter if you raise it to the 5th power or the 500th power. I can give you either problem just as quick, as long as you give me a calculator, with a 5 millionth power. The whole key is that your complex number has to be written in a certain form to use this. What form do you think we have to use?
Trig form?
We have to use trig form. Yep. So let's pretend like we had a complex number with a radius and an angle. So that's trig form. And we're raising that to the nth power. I don't know if de Moivre's theorem works if n is not an integer. Like if you want to raise it to the 3.5 power. I don't think it does. We're not going to be raising to non-integer powers anyway. But that would be something worth knowing for sure. All right, so to raise a complex number to an integer power, we have to do two things. We have to modify the radius and the angle. Here's how you modify the original radius and the original angle to raise it to a power. All you have to do is take your radius, raise it to the power, and this time take your angle and multiply it by the power. And that takes the place of having to write down n copies of what you want to multiply and then foiling it all out. You just have to do two things. Radius to the power, angle times the power, and you're done. So let's try that on the one that we just did. Now, the disadvantage to the one we just did is it's not in trig form, so I need to put it in trig form first and then go from there. Yeah.
So the n inside the parentheses, is it like cosine parentheses n times the degrees?
Yeah.
Okay.
Like that. So cosine of your angle times the power you're raising to. So let's try that here. And to be accurate, anything that we have to round, we'll do 3 decimal places, so the answer comes out pretty close. Okay, 2 plus 3n. What's going to be my radius in that triangle? Square root of 13. Okay, we're not going to round. So there's my radius.
Wait, alright, is that just like something that you remember?
I don't know. How do you do it?
I squared both numbers in my head and added them together.
Yep. So we've got Pythagorean theorem.
Okay, it's just. Okay.
4 plus 9 is 13.
And what about the angle? What's my formula to get the angle here?
It's in the first quadrant, so that's just inverse tangent whatever x.
Inverse tangent.
Which would be 3 over 2.
That's not going to come out nice, so we are going to round that to several decimal places. So 56 point, well, I'll just say 3.1 because it's so close to 3.1. I was going to do 3 decimal places, but that's what it would be to 3 decimal places. 56.31. Okay, so let's write our trig form. R cosine 56.31 plus I sine 56.31. And we're going to take all of that. And did we do the third power?
Yeah.
Yeah. Let's use de Moivre's theorem and see what we get. So, what am I supposed to do with my radius and my power?
I was supposed to put the power up to the radius.
Yep, so raise the radius to the power. Now this is not a nice answer, so we're going to use several decimal places. 46.872 times the cosine of, and what am I supposed to do with my angle and my power? So 56.31 times 3 gives me an angle of 168.93. Now, how do I get that into standard form to see if it matches what I have there? Distribute. So 46.872 times cosine 168.93. And we get negative 45.99999, which is basically what number? There's my negative 46. And let's do 46.872 times what to get the imaginary?
What? Just for you. Oh.
Sine 168.93. And we get 8.999, which rounds up to 9. So, doing what I just showed you in trig form gave us exactly the same answer as in standard form. Now, I would probably argue that you could just do this by hand faster. 2 plus 3i, FOIL it, just don't make a mistake, and get negative 46 plus 9i. But if this power was like 9 or 10 or maybe even like a 5 or 6, it's definitely going to be faster to take 2 plus 3i, write it in trig form, and then use de Moivre's theorem. Because once you get to powers that are like 6, 7, 8, you've got so much foiling, the chances of a mistake are much higher. And you've got so many decimals going on that if you're going to FOIL it out, you're going to keep foiling more and more and more decimals. Your answer is going to get less and less accurate. If you started with one with decimals. If you didn't have decimals to start with, then that wouldn't be a concern. But it would still take a long time. Any question on that? All right. Let's do something a little harder than that. Let's do that this one. So that's a little bit more unreasonable to try to do by hand.
Yeah, okay.
Because now you're going to have to write it 7 times and FOIL it. And you got square roots in there, so it's going to be a mess. So, what do we want to do with 1 plus root 3i? Yep.
Graph it or find
Yeah, we want to put it in trig form. If you can do the Pythagorean theorem, just looking at it to get the radius in your head, that's fine. If you want to graph it, that's fine too. So there's your triangle. Real part is 1. Imaginary is root 3. What's my radius?
2.
The I just tells me that I go up. I is just y-axis or vertical axis movement.
Oh, that's right. Sorry.
Remember, this is your real axis.
Yeah.
This is your imaginary. Sorry, what's my radius? 2. 3 plus 1 is 4. You take the square root. So 2. And what's my formula to get theta?
Inverse tangent of square root.
Inverse tangent of y over x. And we just did this. What's the inverse tangent of root 3?
60.
60, yep.
Yeah.
So my angle is 60. So nice, very nice numbers this time. So 2 cosine 60 plus I sine 60. Now raise that to the 7th power. Okay. What do I do to get my radius?
Raise it to the same power.
Raise what to what?
Raise 2 to the 7th power.
2 to the 7th power, and 2 to the 7th is 100 what? 128? Yep. So 128. Cosine. How am I going to get my angle? 60 times 7, which is 420. But that's bigger than 360. So it's minus 360. That's how they usually do it. And the angle ends up being exactly what we started with. That's fine. Just the way it happens.
Really?
Yep. But that is definitely correct. So when you multiply 60 times 7, you get 420, but then when you subtract 360, it brings it right back to 60. Way faster. We'd still be foiling it if we had to write that out 7 times. Or even if you wanted me to do to the 700th power, we could have done that just as quick as we did this problem. Just need a calculator. Any questions on that? All right, so here's one that's already in. No, that's not in trig form. That's standard form. So let's try this. What quadrant am I in this time?
So that'd be this
Second quadrant. Each side in this triangle is the same, which means, and that means something. How long is each side?
root 2.
2 over 2.
It's 45 degrees. Does that mean that we already just know the angle?
Yeah, we do.
It's a special triangle.
It's a special right triangle, so we know that's a 45, so we know the angle to here is 135. Okay. What's my radius, though? Yep.
It's just 2.
Nope, it's not 2. It is a nice number, though.
Really?
Oh, yeah. Yep. 1. When you square root 2 over 2, you get 1/2. So when you square this, you get 1/2. When you square that, you get 1/2. 1/2 plus 1/2 is 1. And then take the square root is 1. So to write this in trig form, you really don't even need to put the 1, but it's just, I'll put it. It's 1 cosine 135 plus I sine 135. And we're raising that to the 8th power. So when we raise that to the 8th power, what's my new radius?
Still 1.
It's still 1, because it's 1 to the 8th power. So it's still 1. And how am I going to get my angle?
8 times 135.
Yep, so we get 135 times 8. Pretty big. So what can we do to make it smaller?
Can't you subtract 360, right?
Yep, we could even subtract it again.
Wait, so why do we make it 135?
Because that's the angle. That's the angle.
Oh.
From 1.
Yeah, that's right. Okay.
So we got 1080. We can subtract 360. We can subtract 360. We could do it again.
And it's 0.
So the angle is 0. So what does that tell you about if you were to graph this point? Where do you think it? Anyone have an idea where it would end up? I'll change it to standard form if you don't know. Does anybody think they know? Yeah?
The origin.
Well, think of it as it's going to be like on a circle somewhere. It's going to be on a circle of radius 1. So it has to be on the perimeter of the circle. Well, what's the... It's going to be right here. That's where it would be. Change it to standard form. It'll make it easier to see. What's the cosine of 0?
1.
Right. Cosine of 0 is 1. And what's the sine of 0? 0. So effectively, because the sine is 0, that wipes out the imaginary part, which means there's no vertical movement when you graph this. So now you're just left with 1 times 1, which is 1. If you want to think of it as imaginary, it's 1 plus 0i, but I usually don't write that. There you go. So,
That whole complex thing
how did I get 1 here? What did I do? Like, what did we start with, and how did we get a 1? What was
the starting?
Yeah, what was the very first thing we did?
We found the radius.
Okay, so yeah, after we found the radius and the angle, so after we got to this step,
Okay. All
what
right.
did we do with what I'm pointing at?
We raised it to power of 8.
We raised it to the power of 8. How would you undo raising something to the power of 8? You take the 8th root. So if you took the 8th root of what I'm pointing at, what do you think you get?
1? No. Right, yeah, there's 1.
Well, there's 8 answers, but specifically there's one answer that I think you should see that you would get. What is it?
Negative.
Well, 1 and -1, yes, those are 2 out of the 8 answers. But there's a third one that's right up there.
Where'd you get negative?
Is it added to?
What's that? Because if you raise this to the 8th power, you get 1.
Oh, yeah.
Then if you take the 8th root of that, you must go back to where we started with. So when you're finding 8th roots, there are 8 answers. The 8th root of 1, you guys said was 1, that's right. You said -1, that's right. But then there's 6 other answers, and they are all imaginary. And there's one of them right here. We're not going to talk about how to find the other 5 in addition to the 3 that you mentioned. But that's the opposite of Moivre's theorem, taking that number and then taking a root. Okay, any questions on that?
Well, but is saying that is a different answer than up this to the 8th number?
So when you do roots, it can get to be a lot of answers because whatever root you're looking for, it has that many answers. If you're looking for a square root, you've got 2. If you're looking for an 8th root, you have an 8. Usually I don't go above 3 or 4 when I'm teaching. Because if you can do 3 or 4, you can do 40 or 50. It just gets very repetitive once you know how to do it. Okay. So like this problem, if you were going to find the 5th roots of this complex number, there'd be 5 answers. Okay, so let's see about... So that's the homework for tonight. The first part is on multiplying and dividing. The second part is on de Moivre's theorem. And the topics that are on the test, I will do those right now.